Welcome everyone. We are students from Bachelor of Physics program at UPM, currently taking modern physics. In this video, we will explore the theory of hadrons and their applications. Humans have always wondered about the smallest units of existence. Around 400 years before centuries, the Greek philosopher Democritus proposed the idea of atoms, meaning indivisible. Although he couldn't prove it, his concept resurfaced in 1803 when John Dalton theorized that everything is made up of atoms, and chemical reaction involve fixed ratio of these particles. In the early of 20th centuries, Ernest Rutherford and J.J. Thomson discovered subatomic particles, photons, neutrons, and electrons, occupying just 1% of the atom space. Later, these scientists, using the Large Hadron Collider, found that even these subatomic particles are not the smallest, but they are made from smaller components called quarks. Today, we know that subatomic particles form various combinations of quarks. Hadrons is a special category of these particles, interact via strong nuclear forces. Let's dive into the quantum world and explore hadrons.
So, what are hadrons exactly? Well, the best analogy is a molecule for elementary particles. All hadrons are composites of two or more quarks, and can be grouped into two groups, baryons and mesons. However, before that, we have to know what the composites are exactly. The elementary particles are divided into two groups, the fermions and bosons. Each group has their own distinct characteristics and interact with different fundamental forces. However, in both groups, there exist elementary particles that are only made of quarks, and thus we group all these particles together in a group called hadrons. Next up, we have the baryons, the particles who are both made of quarks and are fermions. Baryons are usually made of 3 valence quarks, hence the name triquark. They make up both protons and neutrons and are extremely common as a result. Baryons also interact with the nuclear strong force. Secondly, we have the mesons, the particles who are both made of quarks and are bosons. Mesons are made up of quark-antiquark pairs, thus they have equal numbers of quarks and antiquarks. Mesons are usually the results of high-energy particle collisions and are rare to find otherwise. Mesons interact with both the nuclear strong force and the weak force.
For the latest technology related to hadrons, we focus in its medical applications. Hadrons therapy is also known as particle therapy. It is the cancer treatment that utilizes charged particles such as protons and carbon ions. For example, Med Austron facility in Austria, carbon ion therapy has been used effectively to treat tumors near vital organs. According to Kaneshka in 2024, the advantages of proton carbon therapy versus traditional method is the first, protons and carbon ions deposit most of their energy directly in a tumor with minimal acid dose. After the break peak, which is the maximum energy deposition, radiation dose quickly falls to zero, less damage to surrounding healthy tissue. The practical treatment benefits is hadrons therapy is more precise targeting of tumors, significantly reduced side effects in the treatment, particularly useful for testing deep-seated tumors, and it is more efficient than traditional experimental methods of treatment planning.
Next, we are going through the enhancement by hadrons in detection technology. There were many challenges of hadron analysis. One of them is a non-electromagnetic component which does not contribute to signals, invisible energy. Its solution is to use compensation techniques to design a calorimeter to equalize the response to electromagnetic and non-electromagnetic components. For example, is the Zeus uranium scintillator calorimeter. Next challenge is calorimeter responds differently to the electromagnetic and non-electromagnetic components due to non-compensation issue. Its solution is by using dual readout calorimetry, which is used to sensor separately measured electromagnetic and non-electromagnetic components at the same time. For example, is the dual readout calorimeters. Last but not least, the proportion of energy for electromagnetic and non-electromagnetic can vary widely in a short time. event fluctuations. Its solution is to use the time structure exploitation, which helps to analyze the time distribution of shower signals. One of its examples is the tile calorimetry.